All right, let's dive into the world of fluid mechanics. It's a field where we use a lot of math to figure out how things move and behave. But behind all those complicated equations, there's actually a simple, really powerful grammar that holds it all together. Today, we're going to explore that fundamental language, the quantities and units that are the absolute foundation of everything we do here.
But first, let me ask you a question. What do you think is a shockingly common and totally preventable reason for some of the most catastrophic failures in engineering? I'm talking collapsed bridges, lost spacecraft, the really big stuff.
Well, the answer isn't always some deep, complex misunderstanding of physics. A lot of the time, the mistake is way more basic. It's a simple but critical error in the language we use to describe the world, the language of units.
Yeah, this world of different measurement systems can feel like a total minefield. But believe it or not, there's a core principle that brings some much-needed order to all the chaos.
And that principle is called dimensional harmony. It's a really simple but profound idea. In any equation that actually means something, every single term has to have the same dimension. You can't add a length to a time or a mass to a velocity. It's just like they say, you can't add apples to oranges. Every piece of the puzzle has to fit.
So, if dimensional harmony is the grammar, then what are the letters? Well, the language of physics is written with a surprisingly simple alphabet. Let's take a look at these basic building blocks.
We call them fundamental quantities. And in mechanics, pretty much everything can be described using just three of them: mass, which we represent with the dimension m, length, which is L, and time, which is t. This is it. This is the essential alphabet for building our entire understanding of the physical world.
And from here, you can see how these fundamental letters combine to form words, what we call derived quantities. For instance, velocity. What is it? It's just the length you traveled over a certain amount of time, right? So its dimension is simply L over t. Or how about density? That's just mass per unit of volume, and since volume is just length cubed, its dimension becomes m over L cubed. See? It all builds from those three basic letters.
Okay, so here is where the trouble can start. While that alphabet of mass, length, and time is universal, we humans went ahead and created two different languages or systems of units to actually measure them.
On one side, you have the International System, or SI, which is pretty much the global standard for all science and technology. And on the other side, you have the United States Customary System, or USCS, which, as the name suggests, is still widely used in the US, especially in engineering fields.
Let's put them side by side. For length, SI uses the meter. USCS uses the foot. Okay, different but manageable. For time, hey, look at that. They both use the second. Easy enough. But then we get to mass, and this is the critical difference, and frankly, a huge source of confusion. SI uses the kilogram. The USCS, on the other hand, uses a much stranger unit, the slug. And that one key difference in the base unit for mass causes a ripple effect through all the other derived quantities. In SI, the unit of force is the Newton, but in USCS, it's the pound force. For pressure, SI uses the Pascal, while USCS uses pound force per square foot. It's so easy to see how you could mix these up if you're not careful.
So we have to zoom in on this because it is, without a doubt, the single biggest point of confusion when you're working between these two systems. It is time to finally understand the slug and the pound.
I know, the name itself just sounds weird. Is it some kind of garden pest? Not quite. In the world of physics and engineering, the slug has a very, very precise and critical meaning.
Okay, here's the crucial point to remember. The slug is the USCS unit of mass. It's actually defined right from Newton's second law. F equals ma. 1 pound of force, when you apply to 1 slug of mass, will make that mass accelerate at exactly 1 foot per second squared. It's the specific unit of mass that makes the math work out cleanly in the USCS system.
And this right here is the most important takeaway. Mass, which we measure in slugs, is the intrinsic amount of matter in something. It's what an object is. Force, measured in pound force, is an interaction. It's a push or a pull on an object. In everyday conversation, we get sloppy and just say pounds when you really mean mass. But in engineering, you absolutely cannot do that. You have to be precise. A pound is a force, a slug is mass. Period.
So, why have we spent all this time on slugs and pounds and meters and feet? Because it all comes back to that question I asked at the beginning. It all comes back to building things that work and, more importantly, building them safely.
So, let's just recap the absolute must-knows. First, dimensional harmony is not optional. Never, ever mix apples and oranges in your equations.
Second, always remember that in the SI system, the base unit for mass is the kilogram. Third, in the USCS, mass is the slug and force is the pound force. And finally, the most critical lesson of all, mixing these systems without being extremely careful with your conversions is a direct path to failure.
So the next time you approach a problem, remember that the units are not just some labels you tack on at the end. They are the very language of physics itself. And speaking that language fluently and consistently, well, that's what separates a solid design from a disaster. Because in fluid mechanics, consistency isn't just a preference. It is the absolute bedrock of safety and success.